Good day, everyone. It is nice over here for you and I because learning never ends and education is the key to an impactful life. My name is Anthony Nathaniel.
Good day everyone, and welcome you back to another episode of our physics course for secondary school. And today we are going to be discussing the description and property of fields. In the previous episode, when we were talking about electric charges, we didn't talk about the fact that those charges, the forces that they exert on one another, they constitute a field. So a field is basically a region of space under the influence of some physical agency such as gravitation, magnetism, and electricity. There are many types of fields, but for this chapter and this episode, we are going to be dealing basically with gravitational and magnetic fields. So basically, a field is basically a force whose source does not require contact with the body to which they are applied. So these fields, whenever they are applied to any other body or object, they do not require contact or charges, so any other particle. So this force field, we have scalar force field and we have vector force field. A scalar field is one that has only magnitude but no direction, but a vector field has both magnitude and direction. Example of scalar fields are temperature, energy, and density. But vector fields, they have both magnitude and direction. Like gravitational field has a direction, magnetic field has a direction, and electric field has a direction. So let's talk about this in more detail. And let's talk about gravitational field. So for all of us earthlings, it is kind of like a common thing. When you throw a stone up, it comes down. When you throw a ball up, it comes down, right? Now, before Newton, it was kind of like an ordinary thing, but when Newton discovered the law of gravitation, it changed the perspective. Now, I want to talk about the gravitational field. It is a convenient and informative method of describing the gravitational attraction of one body for another at a distance. It is a force field that influences the motion of the object in space where it operates without coming in contact. So any force that doesn't come in contact with what it is acting on is called a force field. Now, gravitational fields act over a distance. For example, when you have a spacecraft in space, the force acting on that craft, it has it at a distance from the center of the Earth. Now, the Earth attracts every object existing in the Earth's gravitational field. This attraction is called the gravitational attraction. And now, this attraction, as I said earlier, because it has a force attached to it, it also has a corresponding acceleration, which is due to the Earth's gravitational field, and it's called the acceleration due to gravity. Now, if you are adept in physics, you would have known that the gravitational attraction or the acceleration of gravitation is equals to 9.81 meter per second squared. Now, this acceleration due to gravity, it is uniform at a given place and it is constant for every body, every particle and body. And so because of this, when you have bodies, no matter their masses, when they fall together from the same height, they will reach the floor in the same time. But this is only true in a vacuum, because when you throw it in air, the bodies, due to air resistance, the one with the higher surface area will get there slower than the one. Now, we not only have gravitational force and field, we also have magnetic forces and fields. Now, this magnetic force, it occurs in a pole of magnet. So you can say we have a bar magnet and a horseshoe magnet. It doesn't matter the shape, but the pole of the magnet is the portion of the magnet where its magnetic attraction appears to be strongest. So as a kid, if you've played with a magnet, you see that when you bring two of them close together, at times they attract and at times they repel. Now when they attract, it means that they are on like poles that are placed adjacent each other. But when they repel, it means that they are on like poles or dissimilar poles placed adjacent each other. Now there are only two kind of poles that we can ever have in a magnet, and they are the north poles and the south poles. Now this was the force of attraction and the force of repulsion that I was talking about earlier. So these are when you have a north pole and inside south pole beside each other, there's an attraction. But otherwise, when you have a north pole and a north pole, or a south pole and a south pole, there's a repulsion. Now we humans, based on our researches in science and all the rest, we've learned to understand that this field, they have their path and this part they can be described by a particular set of um, um, parts known as the magnetic line of force. And this line, you can see this is the way it follows. So they always move from the how they go from left to right, that's from north to south pole, because these fields, they always go around the magnet and they are concentrated. The field lines, you can see that the regions at the poles are very dark. So that's how it generally looks like in the magnet. So when you see a magnet next time, just know that these are the field lines are around the magnet. Those magnetic lines described earlier, they can be defined as the lines along which a free north pole would move if placed in the field, or a line such that the tangent to it at any point gives the direction of the field at that point. So these two definitions means that the magnetic line of force can be seen as the line along which, when you place a free north pole, a single north pole, and you place it in the field, it will move along that line at any particular instance. So all those instantaneous parts along which it move, when you join them together, you get the magnetic line of force. Or you can also see it as the you can see it as a line such that the tangent to the line at any point gives the direction of the field at that point. So those are the two ways you can view it. Either way, it depends on your understanding.